So this is the first class of 53707 Robot Systems Programming. I'm starting screen capture partway into the talk, about 20 minutes in. Sorry about that. So you have JCard access to Wyman 170. I'll give you JCard access to the building shortly. If you have any problems with any of the equipment, please let me know, and we'll get it fixed. And don't wander away from a machine. Let it screen lock, because then what somebody will do is they'll shut down power on the machine and reboot it to get you off. Let's see, the repository that we'll push to for the assignments is getteach.lcsr.jhu.edu, and there are instructions here on how to activate an account. This is ephemeral. It'll be wiped at the end of the semester, so any stuff that you want to keep, you want to pull off that repository before the end of the semester. So that's, I think, the basic course overview. Any questions about the course organization? Yes?
Do your equipment always log into the Wi-Fi? Do we need to sign into the Wi-Fi?
You don't need to. It's optional. So if you want to, if you want to browse the things that are going on that I'm publishing in my examples, then if you have ROS installed and if you put this as the last couple of lines in your .bashrc, then your environment variables will be set properly. And when I, for example, do ROS topic list to get a list of the topics that are being published, then there they are. Or I want to do ROS topic echo edumit So this is the command message that's being sent to the edumit. There it is. And so when I drive forward, you can see that there's a positive X, minus X. And so if you set your environment variables and you're on the same subnet, then you can go along and see what's going on with me. You can see it all on the screen. Okay. Questions? How many? I gave an overview of ROS in the LCSR seminar series in November. How many folks made it to that lecture? About half. Okay. All right. I think I'm going to give students have told me in the past that it wasn't until the third or fourth week that they kind of understood why it was that we were here and what we were intending to do. So the next thing I'm going to do is give a short overview of ROS and to try to get the big picture. And so window. So thanks, Tyler. Good luck. I sent around in an email today that if you want to pull down a PDF copy of this talk, you can. The reason that you might want to do that is that there's a bunch of URLs that are embedded into the PDF, and so if you want to click through to the URL that's referenced, then you can do that. So this is just an overview of the robot operating system and things that we're going to be covering in this course. And my goal in this is to try to do a kind of a big picture motivation for the course. So outline of the overview is I want to talk about what I do and ROS core components, the larger open source ecosystem, design and development pattern, and three of the most important tools, RViz, TF, and Gazebo. So on that overview, I do robot dynamics and performance. I work in robotics and performance environments, so stress robots, robots that have automation. And I've been teaching this course for 5 years. This is a picture from last year. That's Nicole and Kevin with a robot that played chess against you and moved pieces. This is a team, Nick and Lydia and Andrew, that did a flying robot that flew around and landed on moving turtle block here over in a previous building. This is the class, not last year, but 2 years ago. So what is ROS? ROS is a middleware. It's not really an operating system. It consists of something called ROS master, and in any ROS ecosystem, there's one or more ROS masters running. And they are a process that coordinates communication, and it also coordinates things like coordinated communication, coordinates logging. And a ROS ecosystem of a robot application running ROS typically has many separate processes that run as individual mains. So they're separate processes running in separate virtual memory spaces, and they're communicating to them between themselves over the network via TCP/IP or UDP using what's called a publish-subscribe model, topics, messages, and actual parameters. So you've got a bunch of processes that are talking to each other, sending data back and forth. There are introspection tools for messaging, and there are standard message types for things like strings, arrays. There are standard message types for sensors like a GPS or a camera, and there are standard message types for actuators, such as a joint that's for control. There's a parameter system for initialization. There's a system for recording messages and playing them back. Right now, ROS is an insecure system, so there's no the communication between nodes is not encrypted, and you can go into a system right now. To those of you who are logged into the system, if you plug in your own joystick and run your own joy node, then you can take control of the robot. It's an open system. So the only way that you can have security in ROS right now is by having a subnet which is protected. The perimeters are protected. And ROS supports C++ 3 and 11, Python, and Lisp, and see more at ROS.org. The ROS core components. ROS master is the single process that provides for naming and registration. And the role of the ROS master is to, there's one ROS master that's running normally. You can have multiple ones in some instances. And we can run one right here. So I'm going to kill the program that's running on the robot. And it falls down. And so up here, I can run a ROS master by giving the command ROS core. And in another window, I can type ROS topic. ROS topic list. And there are two topics that are being published right now by ROS core. ROS core and ROS master are synonyms. And then when I run other processes, so for example, when you're using ROS, by the way, you end up having lots and lots of windows. And my preferred terminal emulator is called Terminator. And so I set my default terminal emulator in Ubuntu to be Terminator. And you can do things like, add and split windows. So we can do things like split horizontally, split vertically, delete. So on the TurtleBot, I'm going to log into the TurtleBot on this bottom window. So I'm going to say SSH. The IP address of my TurtleBot is 192.168.10.102. So you guys can log in if you want. Don't do anything drastic. And the password is TEMPPWD. And here, I'm going to run, and I'm going to run the robot balance program. So that program is running on that machine. It's balancing. And if I run corresponding ROS node to read the joystick here on this machine, then I can push on the joystick and the robot drives. And if I open up another window here, I can say ROS topic list. It's a little slow because it's running on the remote robot. And so these are the topics that are being published. And so we'll get to those in a second. So ROS core is what's publishing the ROS out and ROS ag, and these are diagnostic topics where error messages are logged. So a ROS node, take care, Sam, thank you. So a ROS node is a piece of C++ code that interacts with a ROS system. Now you're all C++ programmers, so this is code for the minimal ROS node. So this is the most minimal ROS node. It consists of, you include ROS.h, you call, and there's a name in the program so that ROS system does not wrap or exclude name. You call ROS init, and you tell, this registers this process with a ROS core. It tells the ROS core that the name of my node is hello world node. And then ROS starts a resource manager. You can consider that magic. ROS info stream logs a single information message into the information log. And so it says hello world once. And then the ROS spin blocks forever until we hit Control C. And then after you hit Control C, it falls through to shut down and exit. So the rules piece of C code. And we will run that. So we're in Hello World tutorial. There's the C++ code. And I'm going to call a shell script, which will, it's just doing a command line G++. So G++ hello world.cpp, output hello world node, and then it references a bunch of libraries, math libraries, ROS libraries, things like that. And so I'm going to split the screen here. Control X O, and we're going to go to ROS topic. When we listed the topics that were being published, one of them was ROS out aggregate, and now we're going to run our simple ROS node. And what it published was a message called that was hello world, and that message was came from a file hello world.cpp main at line 13. So that's a typical logging message that is just for information purposes. And if I run this again, then we'll get it again. So to introspect as to what nodes are running, I'll run this node again. We can say ROS node list, and these are all the nodes that are running. There's a edgemip balance ROS node, that's the balancing program running there. The edgemip ROS joy node, which is the thing that's reading this joystick. Hello World node is running. Joy node is redundantly running, and ROS out, and somebody's got an RQT GUI running, which is fine. We can run another one. And RQT graph. I'll get to RQT graph in a second. So these are examples of the little places for more information right here. So so we have a Hello World node running, and the idea is there's one ROS master, there's many nodes. When a node registers with the system, it tells the master its name, and when a node wants to publish information or offer a service, which we'll get to in a minute, it registers what it wants to publish or services that it wants to provide with the ROS master. And then when another node wants to subscribe to a topic, then it asks the ROS master where that topic is from and subscribes to it. And the ROS master hooks up the nodes and they talk directly. So the actual communication occurs between nodes, but ROS master keeps the master list of what's available and hooks people up. When you're running, you want to, if you kill the ROS master while these nodes are running, then things don't work very well. So you need to kill these nodes and restart them. So when you're doing development, oftentimes you keep a persistent ROS master going, and you can bring down and bring up the nodes individually, and everything will be fine. So we've already looked at some publishing and subscribing. So a topic is the name of a published message stream. A message is an instance is a message that it's like a data structure that has a message type, and it has a support for both publishing it out into the network and subscribing to it. More than one node can publish on the same topic, and more than one node can subscribe on the same topic. It's up to the programmer to keep it straight. The design convention is to publish each topic is of a single type, so we don't publish messages of different types on the same topic. And what I have running now, we'll take a look. Introspection tools. A nice introspection tool is RQT graph. I'm going to kill Hello World and kill this window. So I'll say ROS topic list. These are the topics that are being published right now. And we can run RQT graph. And it's going to give us a graph of what's going on in our system. So what we have running here is, let me change this. So the names line up with what you're going to do this week. What we're running right now is we're running a standard ROS node that I didn't write that comes with the system called Joy node, and it's publishing on a topic called Joy. And we can look at that. Ross topic list, there's the topic joy, and I can say Ross topic echo / joy, and nothing happens. Nothing happens because the joy process doesn't actually publish anything until you move the stick, and when you start moving the stick, it starts publishing, or when you press a button. And so you can see the buttons are here, and the axes in different directions are double precision numbers. And when I stop moving, it stops publishing messages. And I've written a program called edgeemip Ross joy node, which publishes, it reads the joy message, it subscribes to it, and it publishes a twist message on the topic edgeemip command, and my edgeemip balance Ross node is subscribing to it. So we can go take a look at that. Ross topic list. So I can say Ross topic echo edgeemip command, and so that program is publishing things at 10 hertz, even when I stop moving, and it's publishing a twist, and a twist, you can see, consists of 3 linear velocities and 3 angular velocities, and if you've taken Noah's course, you know what a twist is. And right now, nobody's subscribed to anything that the edgeemip balance program, which is running on that thing, that's doing the balancing, but it's subscribing to a command, and if we look here, it's also publishing something. It's publishing edgeemip state, and so we can look at that. And so it's publishing at 5 hertz a message that has whether it's the servos are armed, whether it's running, and the set points for the forward balance and the heading, and these are low-level commands: duty cycle left, duty cycle right, wheel angle left. This is the total number of radians since it woke up. Body frame easting, northing, battery voltage in volts, whether it's armed and running. So this is from the previous message, and this is another message. So this is being published at how fast is it being published? Well, we'll do Ross topic echo Ross topic hertz. So it's going to subscribe to it, and its average rate is 5 hertz. How much data is it? Ross topic bandwidth. So it's not a lot. It's about 400 bytes per second. Notice if I go back to my Ross graph and I refresh, then my edgeemip balance Ross is publishing into the namespace edgeemip topic called state, and there's 2 of us that are listening to this topic. So I'm listening to it, and somebody else here is listening to it. And so this is my command line node that I'm running, and when I kill my command line node right there, and I refresh, then it's going to go away. So other kinds of introspection that we can do is Ross topic info, edgeemip state, and so this tells us a little bit about the info about this message. It's of type edgeemip messages edgeemip state, and if we want to know more about what that message type is, then we can introspect with Ross message show edge-emit messages, edge-emit state. So ROS message is another command line, and it's going to tell us what the data structure of edge-emit state is. So you can see it's all float 32s with 2 booleans on it. So RQT graph, there's a tool called RQT, which is sometimes useful. And when you bring it in, you pull up the plugins on topics and the message topic monitor. That's what we're running right here. So I'm running the topic monitor, and I can monitor the joystick messages, and I got to make them happen. And there they are. Or I could monitor the edge emit state messages, and there they are, being updated at 5 hertz. So you can use this. I don't find this a terrifically useful introspection tool, but some people like it. So I like the command line version, but some people like to poke at a computer with a mouse. So this is a utility called RQT. And so we looked at RQT graph, RQT, ROS topic, and ROS message. And I've handed out a cheat sheet for that. So the core components consist of, in the ROS core components that you installed, or you will have installed shortly, there's several classes of messages, such as sensor messages, geometry messages, navigation messages, trajectory messages, and so on. And they do what you'd think. So if I go to the common messages page, you can see that there's a whole bunch of standard messages. And so, for example, for sensor messages, we have messages for battery state, camera info, compressed image, fluid pressure, luminance, IMU, joint state, joystick, joy, that's one we're using, joy feedback, laser scan, magnetic field, nav fix, that's a GPS, so on and so forth. So there's a bunch of standard messages. And it makes sense to, whenever possible, use the standard message if you possibly can. Because if you use a standard message in your programming, then there's a good chance that RViz will already know how to display that, and other programs will already know how to ingest it or produce it. Yes?
Why does it say indigo?
Sorry?
Why does it say ROS indigo?
Oh, yeah. So nobody's updated the cheat sheet since Indigo. Fortunately, for most of the commands, it's fine. Because the Indigo was not too long ago, and if anybody wants to go in and update the cheat sheet for ROS Connect, that'd be great. And I've been intending to do that, but I haven't gotten around to it. But most of the commands are still valid. So ROS is also a distributed parameter system. I'm not going to spend any time on this, but oftentimes when you run a program, you want to have some kind of initialization parameters, so on any file. So for example, if it's a vehicle, you might want to specify the latitude and longitude of the field of operation, for the depth of where you're going to be going, things like that. Other vehicle-specific parameters would be assigning serial ports or UDP ports or TCP ports or IP addresses. Those are all configuration things that oftentimes you'd prefer not to have hard-coded in your code. And so we'll do a tutorial on parameters this week. Recording and playback of messages. So there's a logging system in ROS called ROS Bag, and we can use it. So I'm going to do ROS Bag. First of all, I'm going to CD temp. So I'm going to start recording the joystick topic using ROSBAG, and it's subscribing to Joy, and it's recording to this file with that name on it. And then I'll just drive around a little bit. And then I'll kill the ROSBAG recording. There it is. And then I can say ROSBAG play, the name of the bag file. And it'll start playing back my bag file just as though I were moving the joystick. It's going to play back all the messages at the same pacing that they were generated originally. And ROSBAG, on all these commands, they have tab completion. So if you tab twice, you can say ROSBAG info, the name of the bag file. And this tells us the duration. I recorded for 6 seconds. This is the name of the bag file. The start and the end time is this time. All times in ROS are UTC, so Greenwich time. Regardless of how you have your local clock set on your computer, ROS bags are always UTC. ROS time is always UTC. And I've only recorded one message here, sensor messages, Joy is the type, and /Joy, and in the 6 seconds that I recorded it, it recorded 447 messages. Yes?
If you use ROSBAG on a virtual machine and your data, say, the duration will be 20 minutes, and you're recording data from several sensors, for example, EM tracking sensors, is that going to be a problem for?
So I don't recommend running ROS in a virtual machine. I mean,
for example, if I have a Windows system and I have to use the Windows system for some, for example, directors, but I also need the computer to log some other data from other sensors that has to run on ROS.
so I would use 2 computers. I've seen so many students who were bound and determined to run things in virtual boxes just waste dozens of hours, it doesn't seem to be a very fruitful effort. So if I had to have a Windows system, there are occasions where we've had to have a Windows system as part of a ROS ecosystem, and what I've usually done then is just have a separate machine and have some protocol they communicate over UDP or TCP. We build some sort of a bridge, in one case we had a virtual Windows box running in a Linux host, and they communicated over TCP, and that worked okay. Not recommended. You can probably get it to work, but it's going to make you cry. ROSBAG. So there are a couple other systems that are published and subscribed systems available. LCM is one. Moose is unique to marine vehicles, and there are lots of general purpose message passing systems. If all you want is message passing, you can stop here. But ROS has a whole bunch of other things in it. So it is currently fully supported in Ubuntu. It's reasonably well supported under Debian. And ROS 2, which is in sort of alpha release, not even beta, ROS 2 is going to support Windows and Mac OS. And so that'll make life easier for some people. ROS has long LTS releases that coincide with Ubuntu's releases. We're using the May 2016. Actually, this is April. Things that are included in the ROS ecosystem is if you've done open source programming, oftentimes what happens is that the different open source systems, packages that you use different build systems, and you have all sorts of problems trying to link them all together. It's fine if you're using IDEN, that looks great. but then you're using OpenCV and some other things, and they each have different build systems, and pretty soon you're having all sorts of conflicts with namespaces and things like that. And ROS includes within it a lot of the things that you probably want to use. It's got all of Boost. It uses CMake, OpenCV, Point Cloud Library, Qt 5, Python Qt, Gazebo, Ogre, and Eigen are all built in. So it solves all the build problems. It all compiles under CMake in one build system. And there's sort of, I would call it crude support for interoperability with MATLAB, with the MATLAB's Robot Systems Toolbox. It's the message decoding on the MATLAB side is a little bit funky. It works, but it's painful. How many folks have already installed ROS on their machine? So most of you, that's great. Okay. So what you saw when you installed ROS and you went through the installation steps on the website is that you had to do this in sudo, created in the system directory op-ROS kinetic. So in op-ROS you can have multiple versions of ROS that can coexist. And the subdirectories of kinetic were bin, etc, include, live, share, and setup.bash. So this is where all the executables were, scripts, header files, link libraries, group by package name. This is all standard message files are here in share. And setup.bash is something that is a shell script that you want to run if you want to be using that version. It sets the environment variables to use that version. And so I usually source that file in my bash RC. And if I so that's the system installation, and you don't ever normally install file here or edit files here. You never edit files in this, and you install it only with sudo apt-get install. So and with the sudo apt-get install ros-kinetic-tab, and you get 1,000 things. And so the tab completion will be your friend if you're trying to find something. So where do we do development? We do development in what's called a ROS workspace. And a ROS workspace is simply a directory that has a subdirectory called /source. And in the source directory, there's any number of subdirectories, each of which is a package or a meta package that contains multiple packages. And you do all your work here in these individual packages. Typically, these packages correspond to a single discrete Git repository. That's the design pattern, and it's a good one. So I recommend you stick with it. These other directories are ephemeral. You can delete them. The build directory is where the packages are built, and the compiled executables and other things are in development. Listed by package name. We're not going to use install much here. But there is a procedure where you can tell if you want to install compiled versions, you can tell where to install it. This is just the default. And so you can see that this all lives under your home directory. And in the devel directory, there's a setup.bash, which will set up environment variables so that the ROS ecosystem knows about your local workspace. And we'll set this up during the tutorials this week. And here's some links. And then within an individual ROS package, within an individual ROS package, so ROS Catkin workspace, source subdirectory, my package, user workspace, sorry. In an individual ROS package. So we're in ROS Catkin workspace. This could be called anything, and oftentimes you'll have different ROS workspaces that you'll switch between when you switch between major projects. Source package name, so this is a package name that I create, and the subdirectory structure, this is the design pattern, is there's a source directory where all your C or Python files live. Your include files live in an include directory with a subdirectory same as the package name. This is where we define custom messages. This is where we define custom services. This is where we put XML files that are called launch files, which launch a series of ROS nodes. It would be tedious if we wanted to run a ROS system that ran 20 ROS nodes. It would be tedious to run them all in command line one after another. And so the launch files are an XML file so that you can launch multiple ROS nodes and do things happen. And scripts is where you have sort of miscellaneous shell scripts and things like that. And hopefully you're all familiar with cmakelist.txt. So cmakelist is used by the ROS build system. It doesn't use it in an entirely standard fashion, but it is understandable and tutorials explain it. And package.xml is a ROS XML file that specifies dependencies. So there's a package system called ROSPack that allows you to understand, you can specify when you create this package, you specify that this depends on PCL and eigen and other packages. And then this package documents that and lets you introspect into the package. And you can say ROSPack package name depends, and it'll tell you what packages it's dependent on. So the whole dependency nightmare and name clash nightmare of using multiple powerful systems like PCL and OpenCV goes away. So there's good tools for introspection with ROS, and one of the nicest tools is RViz, ROS launch. So you're going to be doing this in a later tutorial. So our robot's going to kind of gone walkabout. So RViz is I've been driving around a little bit, so the robot is no longer at the origin. But there's Mr. Robot. And we can look in on her, Miss Robot. And what you can see is that I've defined the kinematics of this robot in a format that we'll learn in, I think, week 3, called the Universal Robot Descriptor format. And I've specified that the robot consists of a box and some wheels, and there's some joints connecting them, and the base has a frame in it. And so you can see that if I zoom in here, you can see there's a frame here in the base, and that frame is remaining it's attached to the blue box, and there's a frame attached to each one of the wheels. And this RViz understands the robot model. It's read the robot description from a parameter called robot description, and it is subscribing to appropriate topics to render the robot in the world. So as I drive the robot around in the real world, it's actually displaying what is known about the robot. So the key to making all these things work is that they use a common message system and they use common message formats. So that's how it all works. And TF is something that we're going to be learning about starting next week. So TF for spatial transformation, or Tully Foote, who originally wrote it, allows you to keep track of multiple frames. And it keeps track of the relationship between multiple named frames, both in space and also in time. So, for example, if you have a camera that takes an image at a certain time and there's a timestamp on it, then you can introspect into the TF system and you can say, give me the transformation between the camera frame here and the base frame at this particular point in time. And it will interpolate back into the historical record of all frames and give you the best estimate of what that is. And so that's really important when you're using sensor messages, because sensors often take discrete messages that are timestamped. So TF is think of it as an interpolation mechanism to buffer and interpolate into spatial transformations in both space and time. And so, for example, this was a project that was done in this course 2 years ago. Some students had a multi-beam sonar that takes, it had 90 beams that go in a fan, and they took that and they put it on the bottom of a styrofoam block, and they use AR tags in a Connect to track the position of this block floating in the tank. And they wrote code that would interrogate the sonar and publish the topic as a scan message. And these are the scan messages from about 100 scans in the test tank over rockets in the bottom of the tank being visualized in orbit. So 3D simulation Gazebo. So this may not work. We'll see. So much for the robot. So in week, I think it's 5 of this course, or maybe it's 6, you'll take the URDIF that you built, and you'll add some physics to it. And this is Gazebo. It's a physics engine. It's running a full physics simulation of this robot. There it is. And this one has a particularly bad balance controller. And we should be able to run RViz. And it's broken. Okay, so not a great demonstration. I'll demonstrate that next time. I'm not sure what's broken. So the point is that with Gazebo, you can do a full physics simulation of your robots, and that can be very useful when you're doing development. Some additional resources. The course webpage is a good place, and I've referenced a couple of books. And if you're interested in where Ross came from, one of the principal creators was Keenan Y. Robick, who was an undergraduate in my lab, who graduated about 10 years ago. Actually, it's in 2003. He went on to work in Ken Salisbury's lab at Stanford, and he and another PhD student were working on personal robots, and they decided that they should go out and get private funding to do this, and they did. And the rest is history. And I just heard from Keenan at the end of the beginning of January. He and his wife just had their first child, and all are well. Anyways, there's a link here if you want to read an origin story about Ross. There's a link you can follow, and it's pretty interesting. Keenan wrote sort of a memoir about Ross in a recent IEEE Spectrum article. So that's it. I'm going to wrap up here with a couple of movies. You've all been very patient. And we didn't actually get into the specifics of this week's assignment, so we'll do that on Thursday. And what I'll do is I'll hit the high point of the tutorials, and I'll give you a demo. I'll show you the code that I wrote to solve the problem. These are some videos from last year's projects in this course. The Nicole and Kevin's project was pretty cool, where they programmed a UR5 and an overhead camera they were running an open source chess playing program, so the robot could play against the human, and everything worked really well, actually. And let's see. So this is Lydia, Ryan, and Andrew, where they've got a quadcopter on the left and a turtlebot on the right. And the quadcopter is hanging out, flying, navigating with respect to AR tags. And the turtlebot starts going in a search pattern with an upward-looking camera, looking for a tag that's in the bottom of the quadcopter. So it doesn't know a priori where the quadcopter is, and they're going to give it a command to start searching pretty quick. And they made a clear plexiglass landing pad on the top of the robot that was just about the size of the quadcopter itself. And man, if I told them, why don't you make this giant landing pad that's like a meter wide? Because it'll make it a lot easier to land on, but they made a tiny one. So when the turtlebot finds that it's under the quadcopter, it sends a message to the quadcopter, and the quadcopter does an autonomous descent and tries to land on the turtlebot. And if I recall correctly in this video, it lands perfectly. It did actually more often than not. Yep. Yay! Jin Bai and Liu Jiang again did a system with the UR5, and they had 3 cameras, and it was the idea was to throw a ball at the robot and have the cameras track the trajectory of the ball and move the ball to intercept it, to catch the ball. Now the UR5 is not a particularly fast robot, as you probably all know. So the real limitation in all this was the UR5, just not fast enough. But so they went through a calibration procedure, and you can see the results in RViz. That's the robot base, and they've got frames for each of the 3 cameras calibrated quite accurately. And this is Liu Jiang just taking the ball and bouncing it throwing it back and forth between his hands. And if you can see in the screen here, it's tracking beautifully in real time. And in the original project proposal, they said, the data's going to be noisy, we'll have to have a Kalman filter, and the data was perfect. They didn't have to have a Kalman filter, they just used the raw data. And it doesn't show up very well here, but if you just squint, you can see the they didn't get it every time, but I was pretty impressed. And they were getting, they were doing sort of frame rate tracking at about 30 hertz with 3 HD cameras. And Ujang just got back he did an internship last summer at DJI in China and then stayed on for the fall. And so I'm looking forward to hearing about his adventures at DJI. And anyways, there are other things. You can look at them online. I think we're out of time. So I didn't get as far as I wanted to today. Next time, I'll spend probably about half an hour going over the tutorials that I want you to do and showing you the project that I want you to code. And then the second half of class will be a clinic, so you can bring your computer, you can start working on things, and I'll be here to answer questions. And by Thursday, we will have figured out what our office hours will be, and we'll go on that. So I'll see you on Thursday. Come see me if you have any questions.
Get your hand out.
There's the power here. Hang on a second.